So, we had started this internal flow in the last class. Okay. So, if you recall what we did in the internal flow, we showed that gamma plus epsilon m du bar by dr is equal to 1 over rho tau naught r by r naught, where this is basically was the tau apparent, this is basically the actual wall shear stress. Okay. So, tau apparent by tau naught is equal to minus r over r naught, that is what you can write, okay, because of the reason that we mentioned over here. So, this is your tau apparent. Okay. Now, in other words, if you now define a variable as y, which is basically r naught minus r, okay, then tau apparent minus tau naught, okay, can be written as 1 over y by r naught. Okay. Therefore, the tau apparent will be equal to 1 over y over r naught, okay, into tau naught. Okay. So, at y equal to 0, that is r equal to r naught. So, it is just the reversing the axes. So, that means now the y is 0 at the wall basically, where r is equal to r naught. Okay. So, at y equal to 0, the tau apparent is nothing but the tau wall, right. At y equal to 1, okay, where r is equal to 0, that is what it implies, the tau apparent is equal to 0. Okay. So, therefore, okay, so these are the two important things. So, at the y equal to 0, okay, you have the tau apparent as the same as the tau wall, and at y equal to 1, okay, the tau apparent basically vanishes. Okay. So, these are basically what we call the linear variations. Okay. Now, tau apparent, okay, can be assumed to be constant, okay. So, that is what we have taken from here. Okay. So, now since tau apparent is assumed to be constant, okay, what can be done is that we can basically integrate this particular form, okay, and we can get du plus by dy plus, okay, as 2.5 gamma r naught into tau naught by rho raised to the power of half. Okay. So, that is what you get, okay, after you take care of this particular integration. After you now you know that what your profile is going to be, all right. Let us push this back a little. So, that is what you get, and this is when evaluated at y equal to r naught, this is the profile that you get. Now, based on this agreement, this analysis, but however, one interesting feature that you see over here, that there is a mismatch of the slope, right. There is a clear mismatch of the slope, okay, at the center line, because it basically tells you that there is a finite slope at the pipe center line, because y equal to r naught, okay, is basically that. So, what you have essentially is that there is a mismatch of slope, or in other words, a finite slope, okay, at the pipe center line. So, you have a finite slope at the pipe center line. Okay. So, that is clearly not correct, because if you recall, for any pipe flow, no matter what the turbulent profile is going to be, there has to be some kind of a inflection point at the center line. Okay. So, this is one of the major drawback when you actually have that your tau apparent is the same as your tau wall. Okay. So, this brings about another empirical velocity correlation, which says u plus is equal to 2.5 ln 3 1 plus r over r naught divided by 2 1 plus 2 r by r naught square y plus 5.5. Okay. So, this is like identical to law of the wall, and it matches the zero slope. At center line. Okay. So, this is an empirical velocity correlation though, whereas the previous one that we showed, that the tau apparent very close to the wall is actually equal to tau naught. Okay. That produces, as we said, a slope which is finite. Okay. So, the normal analysis which states that tau apparent is equal to tau wall close to wall yields a wrong profile. Okay. So, that is what we have seen in the last in the analysis that we just now presented. Okay. So, this is important, and so as you find that there is a lot of empirical relationships whenever you are dealing with this kind of turbulent flow profiles. Okay. Now, let us look at the friction factor. Now that we have done all these things, let us look at the friction factor. So, friction factor is like the CFX in the case of an external flow. Okay. So, what is friction factor? Friction factor is basically your F is equal to tau naught divided by half rho u square, where basically u is the average velocity, if you recall, and u normally will be given as 1 over pi r naught square. It is a double integral u bar r dr d theta. Okay. So, that is the definition of friction factor. Okay. This is the same definition as in the case of a laminar flow, right. So, there is no real catch over here. So, if you assume once again Prandtl's power law, which is 1/7 if you recall, okay, and assume that it holds till u bar is equal to uc and y equal to r naught. Okay. So, assume that it holds till u bar equal to uc and y equal to r naught. So, the Prandtl's power law profile. Okay. So, then what are you going to get? Your profile will be uc being the center line velocity. Okay. So, tau naught divided by rho raised to the power of half. This is the profile. tau naught by rho half by gamma raised to the power of 1 by 7th. Now tau naught by rho, okay, raised to the power of half is equal to u f by 2, okay. Therefore, uc by u f by 2 raised to the power of half is 8.7 r naught tau naught by rho half divided by gamma raised to the power of 1/7. Okay. Now, if you put now this expression back, okay, this expression now if you put it back to the original form of your u, which is equal to 1 by naught square, so you put it back in this particular form, okay, you get your f to be almost equal to 0.078 Reynolds number based on the diameter to the power of 1/4. This Reynolds number is based on your u. Compare it with the laminar counterpart, you will find that it is 64 by RED, if you recall. So, this is basically scales as Reynolds number to the power of -1. So, as you can see, this is a weak dependence on the Reynolds number. This is the same type of dependence that we saw in our previous case as well, okay, right, where we saw that the Reynolds number dependence was kind of very mild. Okay. So, you can take a look at your figure 8.2, okay, of Bejan, where you can see that this gives you basically the friction factor with the Reynolds number. Okay. So, for the laminar counterpart you will have, if I try to redraw it kind of, let us try to do that. Of course, you can still take a look from your book. This is ud by gamma, right, that is the Reynolds number, okay, and this is basically written as 4f. Okay. It does not really matter what you write. Okay. So, it is basically plotted against f versus the Reynolds number. So, it is about 0.1 it starts, okay. This is about 0.01. Okay. So, your laminar profile is going to come down like this. Okay. Well, so this is the laminar profile. As you can see, the drop is very sharp. It is f is basically 64 by RED. So, this scale, because it is plotted with 4f, this will be with respect to 16 by RED, right. Okay. So, that will be the velocity profile. Now, this is basically the Reynolds number is about 10 to the power of 4 right around here. Well, it is a little bit moved from here, let me not just, it is around here 10 to the power of 4. So, this will be roughly around it continues up to about 10 to the power of 3 and a little above, right, which is standard, as you know, around 2000, Reynolds number of around 2000, the laminar profile is kind of reasonably valid, right. Then of course, you have the Karman-Nikrudas type of relationships based on what is the roughness factor, but if the roughness is kind of pretty low, the profile will look something like this. Let me draw it. Something like that. So, this actually kind of merges around 10 to the power of 7. Okay. So, this is about 10 to the power of 4, this is about roughly 10 to the power of 3ish. Okay. So, you know around 2000 it will start to go. So, there is a transition zone right around here, and then the profile is kind of a lot smoother, okay, something like that. Of course, as you increase the roughness, this profile takes different values. So, for kind of a smooth pipe, okay, so that is the kind of friction factor that you will normally get, okay, which gives you roughly a Reynolds number of -1/4. kind of a dependence. That is why the slope is kind of a lot smoother compared to the -1 slope that you would normally have in the case of your Reynolds number. Okay. So, based on surface conditions and other things, you can have a lot of differences, but this is in a nutshell which actually tells you that when you actually have a turbulent flow, then basically this is what actually happens. Okay. Now, you can devise the same relationship from law of wall. Remember, there are two ways of finding the friction factor. In one case, we can find out the friction factor, but just by looking at the assumed velocity profile, which was what was done by Prandtl. Now, there is another alternative by which you can actually look at the same profile, the same friction factor profile from the law of the wall, right. So, that will be the second way. We did the same thing in our in our external boundary layer. Okay. So, there what we found is that the friction factor would be something like this, 1.737 ln Reynolds number d minus 0.396. This comes from the law of the wall. Okay. Okay. So, these are the two interesting things that we can observe. Okay. So, in two ways we have basically determined the same thing. Now, we go to the heat transfer coefficient. Argument. So, you first go to the stage of fully developed. Okay. So, once again we start with the fully developed kind of a flow profile, right. So, the position will be rho Cp u bar dt bar by dx is equal to 1 over r d by dr r q apparent double bar, right. So, this is basically the fully developed profile. Once again we have substituted it by the q apparent, right, because that is, if you recall, that is epsilon h plus alpha, right, that was what it was. Now, if you integrate it up to any r, this is rho Cp u bar dt bar by dx r dr is equal to r q apparent double prime. If you integrate it up to r naught, you would get rho Cp u bar dt bar by dx r dr r naught into q naught double prime, right. Because if you are doing it the integral up to the center line, right. So, it will be naturally equal to the q naught double prime. This is the wall heat flux, this is the apparent heat flux that we can decipher, right. So, what we do is that if you take the ratio of the two, right, these two quantities, let us call this 1, call this 2. So, what we do is that we divide 1 by 2. Okay. So, in other words, you have your r q apparent double prime divided by r naught q naught double prime, okay, that is equal to from 0 to r rho Cp u bar dt bar by dx r dr divided by to r naught rho Cp u bar dt bar by dx r dr, right. So, this is the two divisions that we have done. So, now what will happen is that q apparent double prime divided by q naught double prime is equal to r naught by r 0 to r u bar dt bar by dx r dr to r naught. So, this is just a basic division that we are doing. Okay. So, at this point once again we define y is equal to minus r naught, right, y equal to minus, that is the same way that we defined it in our velocity case. So, this will lead to 1 minus y by r naught should be now equal to 1 plus r minus r naught by r naught, which will give you basically r over r naught, right. Okay. This is what you get. So, therefore, your q apparent double prime divided by q naught double prime is given by some factor m multiplied by 1 minus r over y over r naught. So, where m is basically given as 2 by r square 0 to r u bar dt bar by dx r dr divided by 2 by r naught square 0 to r naught u bar dt bar by dx r dr. So, this is basically that ratio of the two terms that we have written as m. Now, if the pipe is heated by heat flux which is not a function of so it is heated by a heat flux such that that heat flux is independent of x. Okay, so that heat flux is independent of x, that is not a function of x. Okay, so therefore, this leads to your dt bar by dx is also not a function of r in that particular case. Or in other words, what happens is that this term that you see over here, this basically all cancels out. Okay, this dt by dx from on both sides, because this is an integral which is performed with respect to r only. So, therefore, your m based on this assumption, if you apply this assumption, basically boils down to 2 by r square by 2 by r naught square, right, integral 0 to r u bar r dr divided by 0 to r naught u bar r dr, right. That is what we get. So, these two, this is a reduction in the profile based on the fact that your axial temperature gradient is not a function of r anymore. Got it? So, that is an interesting fact. Okay, so so right now in what we will do in the immediate next class is that we will see that how this profile can be kind of adapted, okay, and it can give us some pretty interesting results at the end. But you understand the steps once again to recap it very quickly. Okay, so what we have done is basically after we had done with the friction factor, we have just written the equation for the fully developed flow, okay, and we have just integrated it into two parts, one from 0 to r and from 0 to r naught. One is q apparent, one is q naught double prime. We have taken the ratio of the two, we have defined another variable, substitution basically, and then we have defined that this variable is a function of your m, okay, and this m is basically given by this particular quantity over here. Then we argued that your axial temperature must have been not a function of r. In that case, it just boils down to something like this. Okay, remember the integral limits are different. Okay, so in the next class we will see now how this can be further simplified, so that we can get some insights about what is going on in this kind of a pipe flow. Okay, thanks.